Good morning, good afternoon, good evening, whatever time zone you are presently, and welcome to the final unit, the last unit, which is titled Probability Theory. And we'll be discussing the concept of probability and its usefulness, its application into business decision making. Now, probability is a basic component of decision making. Many decisions in life, we make them under uncertainty. We are not sure of the events of what will happen, the likelihood of something. So we need to understand the likelihood of events, the chances of an event occurring to help us to make an informed decision in our daily life, in businesses, even in government policies and the likes. So the objective of this unit is to present you with basic concept of probability needed for an understanding of statistical inference. We shall introduce the subject by considering the probability that are based on observed data. So what are the learning outcomes? At the end of this unit, you are expected to be able to define various terms and probability concepts, use probability theorem in business decision making, interpret probability distribution in business application, and solving word problems using probability models. What is probability? Probability is chances of an event occurring. Take for example, you are pregnant. It is an early stage pregnancy, you've not gone for any scanning or all that. So the chances are, if you have just one fetus in you, the chances are either you give birth to a boy or a girl. So the chance of a boy is the same thing as chance of a girl. That's what we call probability. So the event, the likelihood of an event occurring, the likelihood that you are going to give birth to a boy, the likelihood that you are going to give birth to a girl, the likelihood that it's going to rain the next tomorrow. That's probability. Now, let's define some terms in probability, because we'll be using them, make use of them as we go on. The first one is sample space. What is a sample space? It refers to the set of all possible outcomes. Like the example I just gave, it may rain or it may not rain. We have two sample space. So the sample space refers to the set of all possible outcomes of a random experiment or process. It is denoted by capital letter X or omega. For example, if you throw a die, 6 fair-sided die, what are the possible outcomes? Either it turn up 1, 2, 3, 4, 5, or 6. For a coin, we have either head or tail. For rain, either it rains or it does not rain. So those are the sample spaces. All events are subset of a sample space. While the set of all possible mutually exclusive outcomes is called a sample space. So each outcome, a boy, a girl, is called simple points, or we call it an event. Event of having a boy, event of having a girl, event of raining or event of not raining. This is what we call sample space and event. So examples. Sample space of a trial conducted by 3 coins. Those is either you have head, 3 of them will turn up head, 2 turn up head and 1 tail. All of them will turn up tail. These are what we call sample space. When tossing a coin, we either have maybe both of them, the first 2 times head, tail, head, tail. So these outcomes, each with an equal probability, represent what we term a uniform space. All of them have equal chance of occurring. But suppose we now have, okay, the chance of head coming up, if it's not a fair die, we now assign a probability to each of them. Let's say 2 heads with 1/4, and 1 head is 1/2, and no head is 1/4. So this shows that this is not a uniform sample space. We call it non-uniform sample space. Now, given any sample space, whether uniform or non-uniform, and the probabilities associated with the points or each event, we find the probability of an event by adding the probabilities associated with all the sample points, which is an event favorable to the event. Let's take for example, a coin is tossed 3 times. The uniform space for this contains 8 points. How do I get 8 points? You toss a coin 3 times. The first one, you are either head or tail. The second one, you may have the first time head, the second time head. The second head or tail or head or tail. For the third time, you may have 3 of them may turn up to be head. You may have head, tail, and all that. So if you do this now, look at this now, you have head, or the second one, head, tail, or head, tail, or head, tail, or tail, head, or tail, tail, or tail, head, or tail, tail. So the total now 1, 2, 3, 4, 5, 6, 7, 8. So total possible outcome is what? 8. Number of sample space now is 8. So we are now, if you want to get the probability of at least 2 tails, minimum of 2 tails. So if you count minimum of 2 tails, this is 1 tail. It's out of it, no tail at all. Minimum of 2 tail. This is 1. Minimum of 2 tail. 1. This is 2. Minimum of 2 tail. This is another one. 3. So that is 3 out of 8. So the probability of at least 2 tail. Okay, 2 tails. The first one, 2 tails in succession. There are at least 2 tails 4/8. This is it. 2 tail. Minimum at least 2 tails. This is 1, 2, 3, and the last one, tail. Because it's minimum. This is more than 2. It at least 2. It can be 2 or more. So we have 4/8, which is finally give us 1/2. But in succession, that is tail follow each other. Here the first one, the tail follow each other, we have 1, this and this. Tail follow each other here, 1. This one does not follow each other. This follow each other, 1, 2, 3. That is, you have 3/8. So that is 3/8. Probability of at least, at most 2 tails. The highest, either you don't have tail, you have 1 tail, or you have 2 tails. At most 2 tails. You count them. This 1. You have 7 of them. And the probability of 2 consecutive coins falling the same. That is, you have 2 falling the same. Either you have head, at least 2 compared to 2 consecutive coins. They follow each other. Head follow head, tail follow head. If you count, you have 6. This is 1. And this is also 2. This head, and this one's 2. This one. This is 3, tail. This is 4, head. This is 5, tail. This is 6, tail, head. So tail follow. So that is 6/8, which will eventually give us 3/4. Events, as I've explained, events is your interest. Like example, we have the first one. Our interest is at least 2 tails. Our interest is 2 tails. The event of 2 tails in succession. The event of at most 2 tails. The event of having a boy event, our interest, what we are after. Okay, the event that it will rain 2 days time. That's what we call events. Type of event, we have complementary events. That is the complement is that it contains sample point of the sample space which do not belong to A. So if you already have events, if the complementary event is the event of rain, the complementary event is not raining. You have an elementary or simple event. This is an event A with only one simple point, just one simple point, simple point. Mutually exclusive event. So two events A and A1 and A2 are mutually exclusive if they cannot occur simultaneously. It cannot occur simultaneously. If you are pregnant and there is only one child, you are given to only one child. It's either it's a boy or a girl. It cannot be boy and a girl at the same time. Suppose since it is one. So it cannot happen, it cannot occur together. That is mutually exclusive event. The opposite is independent event. The probability that all of you will have A, you having A does not disturb your friend also having A in the same course. It's an independent event. So event A1 and A2 are independent if the occurrence of A1 has no effect on the occurrence of A2. Or if and only if P, probability of A intersection A1 intersection A2 equal to probability of A1 multiplied by probability of A2. So let's look at probabilities and proportion of areas. Now, if n, we have n sample points and it comes to an event E, just event E, maybe number of eggs, number of that, and there are n mutually exclusive and equally likely outcome of a random experiment. Then the probability of an event E, as this I told you, event is what your interest, probability of getting a boy, probability of scoring A, probability of B, probability of you getting employed and all that. So probability of events E is the number of events. How many possible events? Remember, okay, how many probability of getting A, getting head? How many head do we have? 3 coin. How many head do we have? Over total number of possible outcome. Number N stands for the interest of events, the number of interest. That's the number of events over total number of sample space. Total number of possible outcomes, that is sample space. Event of interest. Like in the example we have above. In the first one, the probability of at least 2 tastes. Our interest in getting 2 tastes in succession. So that is the event. The total possible outcome, the all possible outcome, that is 8. So that is what we are saying here. So number of events over number of sample space. Now since empty set is a subset of the sample space, as we discussed on that, said that empty set is a subset of every set. So since we don't have, if there is probability of July 35th, that is 0. 0 is whenever you have 0. So probability of an empty set gives you 0. While probability of sure event is 1. So that is why probability value is always between 0 and 1. Why if 0 is probability that event can never occur, an impossible event can never occur, and probability that event will occur is 1. If today is August 10, the probability that tomorrow will be August 11 is certain. That is 1. And the probability of sure events. And probability that event will never occur is 0. That's that. And also that's the mutually exclusive events. The probability of the occurrence of either A1 or A2 is given as probability of A1, A2, which is addition of probability. So, and also for more than 2 events, probability of A1, A2, A3 to AN is probability of A1 plus probability of A2 and so on like that. That is addition law of probability. So if it's a mutual mutually exclusive event. And remember, what's mutually exclusive event? We have it here. Can you see? The occurrence of they cannot occur together. The occurrence of one will prevent the occurrence of the other. So let's see an example. If a person draw a card from a pack, what probability that the card is either an ace or a king? This is mutually exclusive event. Let probability of ace equal to a1, and let probability of king be equal to a2. How many ace we have? 4. How many king? 4. So probability of a1 union probability of a2, probability of a1 plus probability of a2. Just add the probability and I'll give you 2 over 13. Note if a1 and a2 are not mutually exclusive events, then the probability of the event that either a or a1 or a2 or both occur is given as probability of a1 union a2. This is equal to probability of a1 plus probability of a2 minus their intersection, probability of a1 intersection, probability of a2. Let's go to additional law of probability. Look at this Venn diagram. We have probability of a1, which we have, and a1 contains a1 intersection a2 complements. So that is what is not in a2, and everything in a1 intersection what is not in a2, while a2 is a1 intersection a2 complements. You get what we are saying here. So from the Venn diagram above, it is clear that the probability of the union of two events a1 and a2 is the sum of the probability of 3 disjoint events. So what are these 3 disjoint events? So if you want to get probability of a1 union a2, that is the sum of probability of a1 and a2, you will first get the probability of a1, subtract the probability of a1 intersection a2, then get the probability of a2, subtract the probability of a1 intersection a2, which is equivalent as written it as a probability of a1 plus probability of a2 minus probability of a1 intersection a2. So in the same way, the probability of the union of 3 mutually non-exclusive is the same way as we did for 2 events. So probability of adding 3 mutually exclusive non-exclusive events a1 union a2 union a3 is probability of a1 plus probability of a2 plus probability of a3 minus probability of a1 intersection a2, a2 intersection a3, and minus probability of a1 intersection a3 plus probability of a1 intersection a2 intersection a3. So let's see example. This example demonstrates what we are saying. In a single throw of a pair die, what is probability that an odd number or a perfect square greater than 1 shows up? So we represent the event of getting an odd number to be a1, while event of a perfect square greater than 1 represents a2. So but what is our total sample space, all possible outcomes? They are 1, 2, 3, 4, 5, 6. So a1, event of rolling an odd number. What are the odd numbers in this? We have 1, 3, and 5. And what are this perfect square greater than 1? We only have 4. So what is intersection of a1, intersection of a1 and a2? It is there is nothing. They have nothing in common. So that means it is empty set. If their intersection is empty set, that means a1 and a2 are mutually exclusive events. Remember, the occurrence of one does not affect they have nothing in common. They have nothing in common. So that means mutually exclusive events. So number of a1, how many? 3. What's number of a2? 1. Total number of sample space 6. So this is what you need to write out. Parameter you need to write out before you set out to solve the problem. So probability of having what? An odd number. How many odd number? What is the events? Number of events. How many are they? 3. Total sample space 6. So probability of having an odd number, which is a1 equal to 3 over 6, which will give us 1 over 2. Now probability of having a perfect square greater than 1. How many perfect square greater than 1? a2 that we have 4. How many? What is the number? 1. Total possible outcome 6. 1 over 6. So probability of addition of the two, since they are mutually exclusive events, they don't have anything in common. Probability of A union A1 union A2 will be probability of A1 plus probability of A2, which is 3 over 6 plus 1 over 6, which is equal to 2 over 3. And another example, if you throw a dice, you throw a die twice, a fair-sided die twice, the probability that the sum of the spots on the die at 2 throws is divisible by 2 or 3 can be calculated. The first thing to do is to know the total number of sample space. If you try a die, a fair-sided die twice, the first one has 6 samples space, the second 6 sample space. You want to now get the sum. So how do you do it? This is how to do it. Either you have 1 1, 1 2, 1 3, 1 4, 1 6, first one 1, first second 1 2, first one 1, second one 2, first one 1, first second one 3, and so on like that. So the total sample space will be 36. Can you see it? How we arrive at 6? So since we are now saying we are looking of the addition, so we can say 1 plus 1, 1 plus 2, 1 plus 3, and so on till you get to 6 plus 6. Each of them can take 6, 6. So that's 6 plus 6. So the first thing you need to know is total possible outcome. So the probability that the sum of the spot on the die at 2 throws is divisible by 2. Then you have to get the sum and now see how many of them are divisible by 2 or 3. So how do we go about that? Number of A1, 18. That's probability of A1, 18. That is divisible by 2. You have 18. This is 1. This will be divisible by 2. 2, 3, 4, 5. So you count like that and get the total number. Divisible by 2 is A1. Divisible by 3 is A2. So you count them. Divisible by 2 is 18. Divisible by 3 is the 12. So probability is 18. Number of our interest. How many? Our interest is divisible by 2. How many are they? 18. Total possible outcome 36. That gives us 1 over 2. And divisible by 3. How many are they? 12. Total possible outcome 36. We have 12 over 36, which gives us 1 over 3. So we're now looking for the probability that the sum of spot on the die at 2 throws divisible by 2 or. So we have number of A1 intersection A2, either A1 or A2, either divisible by 2 or by 3. A1 intersection A2. How many do we have? We have 6. That are both divisible by 2 and divisible by 3. That are divisible by 2 and 3. We have 6 of them. And so our interest is now either divisible by 2 or 3. 6 of them. And total possible outcome 36. So eventually we get 1 over 6. So they are not mutually exclusive. Hence, probability of either divisible by 2 or divisible by 3 equal to probability of A1 plus probability of A2. Remember I said we are going to subtract their intersection. So probability of A1 is 1 over 2, as we have get above, and divisible by 3, 1 over 3, minus their intersection, which is 1 over 6. So eventually we get 2 over 3. Now, let's move to conditional probability. In many situations, we may have information on the occurrence of a certain event which has already happened, which may eventually affect the occurrence of another event that we are expecting to happen. So, in many situations, we have information about the occurrence of an event and are required to find out the probability of the occurrence of another event B. So, we denote it by P, probability of P, such that A has already occurred. Probability of P, such that A has already occurred. In other parlance, we call it probability that A, such that you have taken without replacement. They call it in some places they call it without replacement. Okay, maybe you are picking something But in general term, is probability of the event such that one has already occurred, probability of B such that A has occurred. So that is conditional probability. For example, a patient comes to a doctor with his family history. We have known before, okay, this person in their lineage, they all do have blood pressure, they do have hypertension. So definitely we take it from there, okay, it runs in their blood. We want to know the probability of the event that he will also suffer from high blood pressure. So the probability of B such that A has occurred is given as probability of B intersection A divided by probability of A. If and only if probability of A is greater than 0. So what you do here is probability of B such that A has occurred is given as probability of B intersection A divided by probability of A. Please take note of this. Probability of B such that A has occurred is equal to probability of B intersection A. Their intersection divided by probability of A, the one that has already occurred. So the above can be extended to the case where B1, B2, we have many events that we want to determine. So we call it a sequence of mutually exclusive events, given that an event A has occurred. So it's given us what we have there. So it's the same formula, but here we are going to get their sum, the summation. Probability of B1 intersection A divided by probability of A plus probability of B2 intersection A divided by probability of A plus probability of B3 intersection A divided by probability of A. So that is how to get if you have sequence of events like that to be determined. So and this is more like just in the general term, like what we have explained. So let's see example here. If a card drawn from a pack of cards is black, let's call that one event A. You have drawn one already, you know it is black. That is event A. The probability of event B that the card drawn is the second card now drawn is ace of spades can be calculated by probability of B such that A has occurred. So we want to get probability of an ace such that the first one that we have picked is black. So what you do is probability of A of B intersection A, probability of getting the ace intersection probability of getting an ace of spade divided by probability of a black. So black card, how many black card? Total number of card is 52. How many black card? 26. How many black ace? 26 also. So to get a black ace, we have 26 over 52, which will give us 1 over 2. Out of 26 black cards, only one is the ace of spade. So the event of B intersection A is 1 over 52. Now, probability of A, the first thing is you get the probability of B, get probability of A, then you now find their intersection. That's exactly what we did here. So probability of B intersection probability of A divided by probability of A. So probability of B intersection probability of A is 1 over 52 divided by probability of A, which is 1 over 52. If you solve that, you have 1 over 26. Conclusion. Here we talk about probability theories, the concept in probability, some terms in probability, and how it can help us to predict the future, to predict what will happen to businesses and all that. Understand what has happened in the past to predict what will happen in the future. These are some of the things we have learned in this unit, that to get the probability of an event of your interest, the number of favorable outcome over total number of possible outcome. That's what we use to get that. I'm talking about the mutually exclusive and non-mutually exclusive events and conditional probability, which given by this formula we are seeing. Thank you for your time and have a nice day.